Hi, my name is Cesar Callafa. I'm going to present our paper, Learning from Incomplete Features by Simultaneous Training of Neural Networks and Sparse Coding. This work is the result of a collaboration with Xiao Wang, Jordi Soler Casals, and Jibin Chao. There are many situations in which we need to train a classifier, but not all the features are available for every input data point. This is the case, for example, of a recommender system where not all the users have fully complete their forms, or in medical datasets where typically not all tests can be performed on every patient. Another case is a self-driving vehicle or robot where objects in the view field can be partially occluded. Let's formulate a problem for a simple case with two linearly separable classes of handwritten digits. Suppose we have access to some features for each of the training data inputs. Our goal is to develop a method to obtain a good classifier, but using only the incomplete observations and their labels. A simple solution to this problem is to use a sequential approach. In a first step, we estimate the missing feature values using arbitrary values or exploiting contextual information. As a second step, we can train a classifier using these reconstructions. However, this approach has limitations. Let's assume we have available incomplete features of two classes that are linearly separable. We then apply some completion method and obtain reconstructions of data points. The problem of this approach is that it could be the case that reconstructions become not linearly separable, so the classifier is impossible to find. This can happen, for example, if we observe half of a digit 3 or 8. If we don't use the label information, we may end up making a mistake in the reconstruction. The key observation here is that we must use label information to reconstruct features properly. There are many more advanced approaches to supervised learning with incomplete features. Garmani and Jordan proposed to use probabilistic generative models in their seminal work in NIPS 1993. This method provided a very elegant approach. However, it is computationally expensive and not suitable for large datasets and high-dimensional spaces. It only considers simple classifiers such as logistic regression. Another approach is to use low-rank factorization models to complete the matrix of features and incorporating label information in this process. This approach is also computationally expensive and uses simple classifiers. More recently, it was proposed to combine Gaussian mixture models with deep neural networks and train the weights and the GNN model simultaneously. The great advantage of this approach is that it allows us to use deep learning models. We propose to combine deep learning with sparse coding for modeling input data, motivated by the fact that sparse coding is actually used by our brain to efficiently represent sensory information. Here we illustrate the behavior of the visual cortex, V1, whose neurons respond to specific orientation patterns in images. Let me show you how sparse representation work. Consider a large dataset composed by small patches in natural images and assume that every single patch can be approximated by a linear combination of few elements in a dictionary of patterns. This dictionary can be derived from theory by imposing properties of signals, as it is the case of the wavelets or discrete Gaussian transform, or it can be learned from data. Mathematically, a data vector is approximated by the product of a dictionary matrix D and a sparse vector of coefficients S, which means that most of its entries are zero. Sparsity is indicated by a constraint on the L0 norm, which is the number of non-zero coefficients. Our goal is to learn the data sparse representation and the classifier simultaneously from the incomplete features. Then we assume that every input data vector X can be written as the product of a dictionary D and a sparse vector S. And we want to learn D and S at the same time that we train the classifier. We propose to minimize a function composed of three terms. The first term is the classification loss based on current reconstruction, and we typically use cross-entropy for this purpose. The second term is the representation error, which measures the degree of approximation at the observed features. And the third term is a regularization that promotes sparsity of coefficients. We develop an alternated minimization training algorithm based on gradients and allowing the application of backpropagation and stochastic gradient descent. We were able to identify sufficient conditions for our method to work. More specifically, imagine that we apply our method, which results in a classifier W and reconstructions of the input data points. If the reconstructed data points are well separated by a hyperplane, then the same classifier also correctly separates the original unobserved data points. A very interesting observation is that we don't require that the reconstructions are accurate as long as the original and the reconstructed data are quasi-orthogonal to the vector of weight restricted to the unobserved entries. We have verified these conditions on numerical simulations. Here we show that the cloud of data points are located above the main diagonal, which means that the condition holds most of the time. It is highlighted that as more sparse the representations are, then the condition is easier to hold. We also compare the performance of our algorithm against the sequential methods on synthetically generated data for different levels of sparsity and two separations degree of classes. Our results show that our algorithm allows to attain the best test accuracy in all the cases. We implemented our algorithm with deep neural networks. We used, for example, a 4-layer convolutional network for the NNS dataset and the ResNet 18 for the CFAR10 dataset. We compare our method against the sequential method and also one state-of-the-art method called neural network GMM, which combines Gaussian mixer models with deep learning. Our simultaneous algorithm outperformed all the other methods. We compared the results on MNIST, Fashion, and CFAR datasets against the case of training the classifiers on complete data, which we call the baseline. Finally, we visualize the reconstructions obtained on incomplete test datasets by using the dictionary trained on incomplete data. We show selected examples of MNIST digits and fashion datasets for random mask and occlusions. Final conclusions. Sparse coding is a powerful model for natural data that can be successfully incorporated into deep learning architectures. And our method allows to overcome well-known issues of previous approaches. It incorporates level information, it allows to implement simple algorithms, and it provides more accurate modeling compared to the GEM model. Thank you for your attention.